So we'll start the next lecture on process creation and destruction. So the way that processes are created in Linux is quite different from the way that they are created in other operating systems. But Linux broadly follows the process creation and destruction mechanism of all Unix-like operating systems. So we will see that this mechanism is an integral mechanism. It is important to understand how this works and basically how a running process works, and then how a running process is actually terminated. So Linux's approach may appear to kind of be unconventional and weird at the beginning, but gradually it will start making sense as you sort of appreciate the benefits of what Linux does. So we need to understand that when the kernel starts, it is essentially not doing anything. So when it starts, it finishes its booting process, but after that, it is not doing anything. So the process with PID 0 is called the idle process. So this process is basically for the purpose of accounting. If you want all the processes to take 100% of the time, then let's say for 50% of the time, you're not doing anything. Then you want to charge that to the idle process, right? So which basically means that for half the time, I'm not doing anything. Then what happens is that you run the init process, which does some work for some of the post-boot work for the kernel. So the init process, as we shall see, is a very, very special process in the sense it starts in the kernel and then it actually becomes the mother process for all user level processes. So in a certain sense, if this is the kernel space, this is the user space, init will start here and then migrate here. So then what we will see is the reason that Linux's process creation is kind of weird is because you take a process and its full memory image and you copy and you create a clone of it. You create a copy of it. So forking, something that we will discuss, is one type of cloning. But broadly speaking, cloning is a very generic mechanism. So fork is only one kind of cloning with kind of its parameters hardwired and set. But cloning is a general mechanism. So the reason Linux's process creation is somewhat weird and unconventional is because to create a new process, you actually create a clone of an existing process, an absolute copy. And then they can diverge at a later point of time. So we will see how do they diverge, if at all. That is one. And when the user space is beginning this version of init, which actually comes from the kernel, this becomes a mother process. Everything else, its child processes start by cloning init. Then the grandchildren of init start by cloning their parents, so on and so forth. So this is broadly how you create a user process tree. And similarly, you can also create a kernel process tree, right, which are kernel threads. So we will discuss this issue in some more detail in the subsequent slides. So what happens is that you have the start kernel function. The start kernel function is a core function that is called at the time of booting, which is to start the kernel, and that creates the init process. So the init process, as we have said, is kind of like a mother process, which basically starts everything. And the init process starts in kernel mode and it goes to user mode. So this is sort of a rare instance where something starts from the kernel, goes to the user mode, because in general, we have seen the reverse. So what we have seen is, in the case of a system call, if let us say we have a user process, so it's a regular process, right? So, so let's just discuss how this regular process is created from init. The way it is created is that you do a series of fork operations. A fork basically clones the entire address space of the parent process. So it creates a copy of the parent process But then you can argue that all the processes will do the same work. But that does not happen because after cloning, you can decide to discard the image and load a new image. All right. So you can say that I will load a new image and I will not do what my parent was doing. All right. So I will do something totally different. For example, my parent could be the shell. So the moment the shell creates a new process, that process will also be the shell. But the new process, the child process, will say, look, I don't want to be a copy of the shell and I actually want to be Notepad. So what it will do in that case is that it will call the exec family of calls, which will replace its image. Instead of a shell, it is going to be Notepad. All right, so far so good. And then the Notepad will execute. So this is basically the way that you start a new process in Linux, where you start by being a copy of the parent. Any fork call, which is a specific case of the general clone call, this clones the parent, creates a copy of the parent. But the thing is that may not want to be a copy of the parent. That is why you call the exec family of calls to replace your image with the image of whatever you want to execute. So now once a process is created and it actually does a system call, so then what happens is that instead of creating a separate kernel thread which has a high overhead, what happens in this case is that the same process kind of transitions into kernel mode. So instead of creating a new separate process, the same process that made the system call, its mode is changed from user mode to kernel mode. So it goes to kernel mode. It can then access a bunch of data and data structures, which are kernel data structures. They are not user data structures, but mind you, the process is the same. It's just that its mode has changed. Then again, when it needs to be restored, you change the mode of the process back from kernel mode to user mode. So in that, the advantage of this is that you do not have to create a separate kernel thread. All right. The same thread that is executing in user mode simply change its mode. It will go to the kernel, do its system call work, and then it is going to come back. All right. So this kind of is an efficient mechanism. Is that clear? This is a very, very efficient mechanism. And this kind of stops you from wasting time and wasting work. So we will now look at the code of the fork system call, which you can try on your own. So these are some 4 or 5 lines of C code. So the basic idea is like this, that we have an original process and it decides to create a new child process. So it calls the fork system call, which creates a copy. The child essentially inherits the complete state of the parent at this point. So it is as if at this point, whatever is the memory state of the parent, the entire thing, lock, stock and barrel, is copied to the child, including the point, the value of the program counter. So the child basically starts at executing at exactly that point, and the child starts. So let us now look at the code line by line. So the way that you do a fork is like this, that you run your program. At some point, you decide that I need to fork. So if you decide to do that at some point, you call the fork call and that creates a child. So here is the magic of the fork. The magic of the fork is that after this point, there are actually 2 processes. Before the fork, there was only one process. After the fork call, there are 2 processes. Both are executing exactly the same piece of code. Of course, their address spaces are now disjoint, but they are at the same point and they are going to execute the same piece of code with the crucial critical difference So it is important that this point is understood with utmost attention, that the fork returns different values for the parent and the child. Because mind you, prior to this, there was no child. After this, there is a child. So after this point, the child assumes that it has been executing from the beginning, even though it clearly hasn't been. But the child assumes that it has been executing from the very beginning, right? It was, let's say, never forked. So what happens is that for the parent, the PID that is returned is actually the PID of the child. All right. And for the child, the PID that is returned is 0. That is how the child knows that I am a child. And that is how the parent knows that I am the parent and who is my forked child. Then what happens is that you test the value of the PID. If the PID is 0, then you can print I am the child. Otherwise, if the PID is non-zero, which basically means that I am the parent process, then I print I am the parent. So this is a quintessential example of the way that the fork call runs, where it basically returns different values to the parent and the child. The child gets a 0 and the parent gets the process ID of the child that was just created. So this is a fundamental mechanism in operating systems, the Linux-like operating systems, where basically you look at the return value of the fork call and then you decide what to do. If I'm the parent, I do something. If I'm the child, I do something else. So now the idea is that you differentiate on the basis of the return values. The question is, what exactly does the fork call do? So all the memory regions of the parent are copied. So whatever is there, the entire memory space of the parent, the entire thing is copied. The state of the process is copied. So every process will have a state: task running, task blocked. Right? Of course, task blocked, you can't fork a new process, but the state is copied. In the sense, obviously, your process has to be running. So that is copied. Task running is copied. The program counters are set to the same value. Right? So it basically, both of them after forking start at the same point. So the program counters start at the same value. And pretty much both, if this is the fork call, both the program counters in the parent and in the child point to the instruction after fork. Both of them. And then they start executing. And clearly the return values are different. That is the only differentiating piece of information, that the return values are different. One gets 0, one gets PID. That is how you get to differentiate. So let us now look at copying the address space. So someone may say that copying the address space is actually very slow. All right. The reason they will say that it is very slow is basically because your address space can be megabytes or gigabytes. So if I want to copy all of it, it will take a lot of time. That is why let us not do any of that. To start with, let us just create a copy of the page tables. So in a sense that if you have a parent and the parent has a page table, and then you have the child and the child has a page table, let both the virtual addresses point to the same physical frame. Both of them point to the same physical frame. So then the address space gets effectively copied, right? Of course, one does a write, other will get to see, which is something that we don't want. So this is a partial solution. It's not the full solution. But we start with just copying the page tables. So then here is the most important mechanism. It's called a copy on write mechanism or a cow mechanism. Of course, people call it copy on write, but they write it as COW. So here the idea is that whenever you do a write, if you are reading, it's fine. Whenever you do a write, you write to a page. So what happens is that you set the read-only bit of the page to 1. All right. So what you do is that in all your entries of the TLB, and page tables, you set the read-only bit to 1. This means that whenever you do a write to a shared page, you will have a fault. The fault will say that you do not have write permission. The moment you have a fault, the interrupt handler will run. All right. So the interrupt handler will run, and then what the interrupt handler will do is that it will actually create 2 copies of the page. It will create a copy of the frame. If the parent was the one who was writing it, the write will go here. If the child was the one which was writing it, the write will go here. But in any case, a copy of the frames will be created and the virtual address mappings will be accordingly changed. So this is called copy on write, where by default, pages are shared between the parent and the child. Whenever there is a write, a copy is created because the parent and the child's address spaces are meant or supposed to be separate. All right, so this is a fast mechanism because in the default case, you can just get the child running just by copying the page table. Right, of course, some bits have to be set to read only. That's the thing, but again, there are shortcuts for doing that. But by and large, the key idea is whenever there is a write, then only you create a copy, otherwise you don't. This is the efficiency generating process in this entire fork mechanism. This is called copy on write. So the question is, how do you know that there is a write? Let us go into the details of this. So the details are that in every TLB entry and page table entry, you store a few additional bits to store the permissions with respect to that page. For example, let's say if a page is read-only, you can have a read-only bit that is set. So a correctness problem that can happen here is that maybe you have a genuinely read-only page, like a code page, and someone is trying to write to it. But the fact is that, making something read-only is only an artifact of fault because you want to capture a write and create a copy. But if it was read-only to begin with, then no copy should be created. So to differentiate between the two cases, you add one more bit. So let us call that bit P2. So that is the name that we give it. Well, let's say P1 is read-only, P2 is this. So whenever we fork a process, we set the value of P2 to 1 for both the parent and child pages, right? The moment there is a fault, right, so the hardware in this case will check either read-only should be 1 or P2 should be 1. Then you will know that, it is there. So the point is that the moment something of this nature is set, then you can have a fault and you can see whether it was read-only or not to begin with. To begin with, if it was not read-only, then what we can do is that we can set the P2 bit to 0. This will indicate that there will be no more faults on this page because I have created a copy. And if I've created a copy, then they can kind of proceed and they can start writing to their private copies of the page. So the takeaway point from this slide is that it is true that when you are trying to write to a page which does not have write permissions, you have to create a copy. But the corner cases when the page was read-only to begin with, from day one, it was read-only. So at that point, writing to a read-only page is actually a security fault. So to differentiate between both those cases, you need an additional bit. The additional bit will say that this has been made read-only just because of the fork. Otherwise, let's say it is not read-only. Then what you will do is, if there is a fault, you will see was it read-only to begin with or it was made read-only to track writes. Essentially, what are you doing? You are inducing these fake faults to track writes. So that is why you have an additional bit whose job is to track writes. And then you create a copy, and this is how you effect your copy on write mechanism. Next, let us consider the case where a fork is done, but the child process decides not to be a copy of the parent, but to execute some other program. In the sense that, as I said, the parent is the shell. The child has an option of being the shell, but it decides to, let us say, become Emacs. So in this case, what you do is that you do the fork call, right? The fork call is done. And then you create an array of 2 arguments. So of course, in the exec family of system calls, there are many exec calls, and they take different number of arguments. If it is a child, right? If I am the child, so what I do is I try to execute the pwd command. Pwd is print working directory. So it just prints the current working directory in Linux. So what I do is I define a constant pwd path. So when I'm doing exec v, I send it a string that points to the binary along with the arguments of the name of the command and bunch of arguments and so on. So you can look at the specific format of this command. All right. So broadly speaking, this command has bunch of arguments, which is the path and name of the binary, arguments to the binary, and if you want to give other arguments on how it is supposed to run. So there, as I said, there are a bunch of exec calls, and all of them take a diverse amount of options. So then it is possible that the child will actually become the pwd command, because that is what it is going to execute. But the parent is going to come here, and it is going to print, I am the parent. All right. So this is a case where the child may decide to replace its image with the image of an existing binary. So far, so good. So the exec family of system calls, broadly what they do is they clean up the memory state. Maybe not all of it, but most of it. Then the entire operative part of the memory state of the executable, which is namely the text section, data section, BSS section, they are all copied from the new binary. The way that you would start a new process, they are all copied from the new binary. The stack and heap sections are kind of initialized in the sense in the reset. So heap size will become 0, stack size becomes 0. And all the sections that had to be read from somewhere, they are read from a file, right? Basically the text, data and BSS. So BSS, of course, it has to be set up. And because BSS is uninitialized global variables, you have to set up the space. But for the code and data section, that has to be read from the image. So all of these things you do, and you kind of set up the memory map of the new process, right? It is true that you are a child and you were created out of a fork, but you have decided that I will not execute my parent's image. I will execute a new image. And that new image is something that you are going to ask the loader to load from a binary. There are other resources that a process typically owns, such as open files, network connections, so on and so forth. So these are maintained by a process even after it decides to change its image, unless it decides to relinquish them, or the parameters of the exec call are such that whatever resources I have, you kindly give them up. Right. So as I said, there are a lot of exec calls, and they have many different options and formats. But broadly speaking, we want the default action is that you change your image, but you hold on to your resources, and your resources are open files and network connections. Then what you do is that you set your program counter to the beginning of the text section. So if this is your code, you start your program counter over here such that it starts executing, and then the new image starts. So as I said, you may be created out of the shell, but if you decide to execute, let's say, Emacs, the entire code and data of Emacs is loaded. And then what you do is that when you start executing from the first instruction of Emacs. All right. So let us look at some of the details of how the fork call is actually implemented. So as I have said, the overall system call, which is kind of the superset, is the clone system call. And there you can sort of create a thread also in the same manner. It is just that when you're creating a thread, you will tell clone that my code section has to be shared. My data section has to be shared, right? VSS has to be shared. Heap has to be shared. What is not shared will be will be the stack and the thread local storage area. So this is where the clone system call can take a large number of arguments. Ultimately, with their arguments and everything, they will end up calling the copy process function, whose job is to take a struct PID of the parent, of course, and finally create a task struct for the child. That is all. So that ultimately, howsoever you reach that point, it is going to copy the process and it is going to create a task struct for the child. So the main aim is that you have a parent's task struct. You sort of want to duplicate the task struct and create one for the child, which the child may decide later on decide to kind of clean it up and replace the image with something else. That is a separate operation. Let us just focus on the clone operation. So in this case, you want to take one task struct and you want to create a copy of it. So to do that, what you will do is you'll create a new task struct by allocating an object. So we will see in the memory chapter how an object in the kernel is allocated. Fair enough. Not now. Then we will set up the 8 KB kernel stack. So for the 8 KB kernel stack, you'll have to go and request some memory manager. What that memory manager will do is that it will give you an 8 KB chunk. The starting pointer to that you will store in your task struct. Then there will be a bunch of architectural state, such as state of the floating point registers, so on and so forth. So those have to be duplicated, replicated, right? Then other kinds of bookkeeping information that a task typically has, that also you will need to duplicate. And you will set the time, the statistics that a child task has run, that time has to be set to 0. Because, it's a new task and you have not run yet. And then some preliminary allocation of this task has to be done to a CPU, right? So you have to allocate this task to a CPU. And once that is done, so basically you'll create a struct PID. And we have already seen in the previous lecture, if a struct PID is created, how you go up the list of namespaces. And in every namespace, starting from the child namespace to the root namespace, you add the struct PID and you get a PID number in each namespace. All right. So broadly speaking, let me summarize the set of steps. So as I've said, in the kernel, you don't do a new or malloc. A new or malloc is a very complex user space operation, and a kernel can't afford this level of memory indiscipline. That is why what you do is that you have separate kernel allocators, which we will discuss later. But in a fork, what are you doing? The parent has a task struct, you want to create a copy of it. So the first is that you need a new object. So you go to an object allocator, ask it for a new task struct. Similarly, you go to an 8 KB stack allocator, ask it for an 8 KB stack. Now this is your new task struct. This is your new stack. Just point to it. Right? You are all done. And then the rest of our bookkeeping information, architectural information, all of that you add. Initialize things because it's a fresh task, right? So it's brand new. So when it is brand new, it's like buying a brand new car. You should start with 0 kilometers, right, as the odometer reading. And then you create a struct PID, start giving the new process numbers. And then you'll have to create the parent-child relationship. So this is there. So we'll look at this. So also, as I said, a process may own resources. What kind of resources? Open files, network connections, maybe some IO related resources like, some access to the hard disk and so on. So all of those you would like to copy unless the new user says, unless the new task says that I don't need them. By default, you copy them. So you copy a connection to an open file. So what is a connection to an open file? So file, as we have discussed, is a contiguous set of bytes on the hard disk. A connection to a file is nothing but a data structure to represent the fact that this process is accessing this file. So it stores some state and some bookkeeping information. Then again, reference to the current file system, signal handlers, all that information gets copied. Also the memory map, right? The entire struct gets copied, and namespace information, etc. All of that also gets copied. So a lot of the additional paraphernalia that we have seen associated with the task struct, all of that lock, stock and barrel gets copied from the parent to the child. Along with that, we also fix the relationships. This basically means that if I am a parent, and this is the, I have a bunch of children that point to me, and also I have a list of, so everybody has a list of siblings, right? Who are my sibling tasks. So what I need to do is that if this is the new child, the child's parent pointer has to be set to the parent, and the child has to be added to the sibling lists of all of its siblings. And all of its siblings, it has to add to its own list. So all of that you will do. If you are creating a multi-threaded process, which is nothing but, as I said, the system call is one, it's a clone system call. If you are creating a multi-threaded process where you have explicitly specified which memory regions of the memory map are cloned and which memory regions are not cloned. So that's all, right? As we have said, a thread and a process are the same. It is just that in the thread, clone has different arguments, whereas in a standalone process, clone has different arguments. The different arguments in a thread basically are that kindly copy the stack, kindly create a separate stack section and a separate thread local storage section, but you can happily copy the rest, right? You can happily create, copy in this case would actually mean share. So what a thread says is that if this is a text section, this is a data section, BSS section. So if this is a thread text section, data, BSS, heap and stack, what clone says is that my stack should be separate, the rest should be shared. So if I am cloning this and I create another task, this part will remain the same. What will vary is the stack. It will have a new stack. So as I said, a thread or a process, it is all dependent upon the argument given to a clone. But if I'm creating a new thread, then it is necessary to set the thread group ID information, right? So we have discussed thread group IDs, thread groups, process groups and sessions. So that information also has to be set for the new task. So if it is joining an existing thread group, then the thread group's ID has to be added to it. Similarly, if it's joining an existing process group, that information has to be added to it, so on and so forth. Same holds for sessions as well. So next, we would like to discuss the different types of threads, right? So Linux distinguishes between user threads. So user threads are threads which predominantly run in user space, but occasionally move to the kernel space to service system calls come back. Then you have IO threads, which are very low priority threads. Well, sometimes they could be higher also, whose job is to access IO devices. And then you have kernel threads, which exclusively live in the kernel. These are threads spawned by the kernel to only do kernel work. So similar to user space clone, there is a kernel clone function to create kernel threads. Of course, both use the same task struct. So user threads and kernel threads use the same task struct data structure that we have studied. The task struct has a flags. The flags is nothing but a bit vector of fields. So that indicates, is this a user thread or is this a kernel thread? So the status is indicated there. And it's just a matter of a single bit. And then, a user thread becomes a kernel thread and vice versa. Then, similar to init in the user space, whose process ID is 1, you have a kthreadd in the kernel space. So we have init in the user space, whose PID is 1. That's like the mother process for all, right? Similarly, in the kernel space, you have kthreadd. So its PID is 2. That is like the mother process for all kernel threads. So there is a kthread create, which creates a kernel thread. So mind you, in the kernel, you don't have kernel processes. I mean, well, every thread is a process, but they are referred to as kernel threads mainly because all kernel processors share the virtual address space. There is a single kernel virtual address space, right? Different kernel processors do not have different kernel virtual address spaces. There is only one. Hence, these are referred to as kernel threads because of the level of sharing. All right. And kernel threads do everything, starting from periodic bookkeeping to timers, interrupt handling, I/O, device interfacing, everything. Kernel threads do a large part of the core kernel work. So now we have come to an end of the process creation destruction part. So we will in the next class discuss context switching, right? Process context switching and how it is done.